Okay, so last class actually happened to be a crucial lecture. So we discussed all the normal forms in the last lecture. Many of you could not attend. I hope you have checked up these slides. So we discussed what are called 2NF, 3NF, Boyce Codd normal form in the last lecture. I gave definitions and examples and all that. Now, a typical situation that we have seen occurring, in the last lecture was that we find certain relation to be not satisfying a particular normal form, and then what we do is we decompose that relation. We kind of redistribute the attributes in the relation into two different relations, and then we see that the same information is represented here, and each of those individual relations are satisfying the normal form that we are looking for. Like for example, if it does not satisfy third normal form, we have decomposed that relation into two, and then we have seen that both of them now satisfy the third normal form. Now, this process of taking a relation and then decomposing it is a phenomenon that is something that we have done several times in the last lecture. In each time when we find that a relation instance, a relation does not satisfy certain normal form. So let us try to make that a little bit more formal and then actually study certain properties of these decompositions. So these decompositions are important. So we will realize during this course of this lecture that all possible taking arbitrarily cut of this of those relations and then bringing them into two relations will not work. We have to look at certain properties before we can do that. Okay, so let us see what is the decomposition in the first place. So if R is a relation scheme, so it has some n number of attributes. If you replace R by this k number of relations R1 through Rk, where each of these Ri is a subset of R and they collectively have all the attributes of R, okay, they collectively have all the attributes of R, then such a replacement of R by these R1 through Rk is what is called a decomposition. Okay. And of course, these Ri's need not be disjoint, they will not typically be disjoint. Okay. So you will need some attribute to be in more than one relation, so that it serves the purpose of a foreign key, primary key reference, etc. Okay. So such a thing is what is called a decomposition. A decomposition is nothing but taking a relation scheme and replacing it with R1 through Rk, and we call this as D, the decomposition, and these R1 through Rk are such that Ri is a subset of R and they collectively give back our set of attributes R. Take the union, you will get back R. For example, in the last lecture we were looking at this relation called grade info, which had roll number, student name, course and grade, and this was satisfying third normal form, but it still had redundancy in that. So we went for a stricter normal form for that, which is called the Boyce Codd normal form. So during that thing we have decompose this into these two relations, roll number, course, grade, and roll number, student name. So here is a example. So we replace this R by this R1 and R2. This is the R and we replaced it by this, and then the attributes are in the two relations. The union is back the entire set of attributes. Okay. Now let us look at can we do this arbitrarily? Can we, are there any problems in this? Is there some systematic way in which this has to be done? These are the various questions that come up in the context of these decompositions. So it turns out that not all decompositions of a relation scheme are going to be useful. We require that these decompositions satisfy certain important properties. So we call, there are two properties, one of them is called lossless join property, and the other one is called dependency preserving property. So basically what we here require is that whatever the information that was present in R, any instance R on the scheme, original scheme. Now if you decompose the relation scheme R into say R1 and R2, what will happen to the data? What will happen to the data? Obviously you have to split the data also. Obviously you have to take the data, project it onto R1, project it to R2 and then create instances of data instances for these two schemes R1 and R2 that we decomposed from R, right. So data has to be also created. The original data, which is the instance R, has to be used in order to derive instances R1, R2. So how do we derive this R1, R2, Rk? Naturally, the most natural way of doing that is to take the projection of the original instance R onto this Ri, right. So that is what we, so whatever be the information that was present in R should now be present in R1 through Rk. Okay. So what do we mean by it should be present in? It will actually be present, right, because anyway you are taking projection of R and then getting these R1 through Rk. So whatever was the tuples that were there in R will automatically, some segments of those tuples will come into R1 through Rk. So each of these tuple that is there in R now will get segmented in some sense actually, right. So a few values of them will go into R1 and then maybe some overlap and then some other segment will go into R2, like that the data will go into all these things. So we will see exactly in the next slide actually whether there can be actually some kind of a loss in this process. Then this is one thing. The other thing is that supposing there was a set of functional dependencies that were holding on the relation scheme R, okay. How do we appropriately translate those functional dependencies into each of these Ri's so that enforcing these functional dependencies on each of these instances or in each of these decomposed relations R1 is equivalent to enforcing the functional dependencies on the original table, original relations. How is it possible? That is another thing. So if a set of functional dependencies hold on R, it should be possible for us to enforce this set of functional dependencies. What do we mean by enforcing? Basically we want to see that the relation instance satisfies those functional dependencies. Either it is satisfying or not, we want to check that. So checking that should be possible for us to, by enforcing some appropriate derived functional dependencies on each of these Ri's. Okay. So these are the two properties that we will look for. Then so we will go into a bit more detail into these things now. Okay. So in this context, first thing is we will elaborate on the losslessness property. That means there should not be any loss in information. Okay. So, let me set that up a little bit more formally now. Let us say we have a set F of the functional dependencies that hold on R, and R is decomposed into R1 through Rk. Now, this particular decomposition is called lossless with respect to this set of functional dependencies, when in any instance, every instance R on this capital R, the scheme that satisfies these functional dependencies, what happens here is that if you take R and project it into R1, project it into R2, project it onto R2, you get little r1, little r2, little r3, little rk, etc. You do a natural join among them, you should get back R. Why natural join? Because attributes are all same, attributes are, there are some common attributes are there. Okay. R has some, say, A1 through A10, So, R1 through Rk will have basically this A1 through A10, right, but then some subsets will be in R1, some sequence will be in R2, etc. So, it is possible for us to do a natural join because there are some common attributes. So, you project the instance for any instance, you take any instance on R, on capital R, and then you get back these instances by projecting them onto R1, R2, R3, Rk, and if you join them back you should get R, because anyway originally this information came from R, so if you join them you should get back R. If this is the case, then we will call it lossless. This looks fair, right? This kind of a restriction looks fair because basically we had some data and now we are saying that the schema is going to be split into two schemas. So, we project the data into two, we should join back, if we join we should get back the original R. Okay. So, that is fair, right, that is what we will ask for in this property. Now, one subtle thing that you have to notice here is that if there is a tuple in the original relation, right, and let us say we have split it into two, let us just for the simplicity sake consider two of them, and so there is some common attribute, let us say. So, we split it into two, right, two tuples have come. Now, obviously if you do a join, because these two tuples exist, you will always get back to your original tuple. You agree with that? You take a tuple in R, okay, take a tuple in R, project it into R1, project it onto R2, you get two subtuples, right. So, it is same tuple became into two different tuples now, one on R1, the other one on R2. So, suppose you do a join on little r1, little r2, because this particular two tuples exist in those individual relations, you will get back your original tuple because these two things join, because they had the same common value anyway. They have some common attribute, let us say they have some common attribute, the common attribute value will go into left hand side tuple, also into the right hand side tuple, and so when you do an equijoin, these two tuples will agree on that common attribute, and so you will get back your original tuple. Is that clear? I can repeat if you want. See, just consider one tuple in the original relation. We are splitting that, we are assuming that the original relation is decomposed into two relations, R1 and R2. So, if you take the tuple, when you project the data, one part of the tuple will go into R1, another part of the tuple will go into R2, and because these two tuples exist in R1 and R2, when you do a natural join between them, you will always get back your original tuple. Okay. So what I am arguing here is that, or telling you here is that this will always contain R, will always contain R. The trouble is, it may not be exactly R, it may contain something more than R, that is the trouble actually. By containing more than what is there in R, it is actually corrupting the information. I will now show you an example where such a thing happens, and those tuples, those extra tuples, uninvited guests for us, something like that, is a trouble for us actually. Okay, here is an example, just look at them. Just look at this, focus on this example. We have ABC and we are decomposing it into AB and BC. Here is an instance A1, B1, C1 and all that. So, I have taken them, projected him here, projected him here. Now, you do a join these two. Now, do a join here. So, A1, B1 joins with B1, C1 and you will get A1, B1, C1, one of the original tuples. But unfortunately, A1, B1 also joins with B1, C3 and then you will get A1, B1, C3, which is actually not there in the original data. Okay. So, it is possible that you will actually get some spurious tuples, these tuples are called spurious tuples. So, some extra tuples will come into the picture. And because of this, we will call this as this particular decomposition is called a lossy decomposition. It is called a lossy decomposition. The original information is distorted and so we will actually call it as a lossy decomposition, even though we are actually having additional tuples. Okay. So, those decompositions that do not have any spurious tuples are what are called lossless joins, lossless decomposition, lossless decomposition. And an easier nomenclature could be that they are called non-additive decomposition. They do not add spurious tuples, so they are called non-additive decomposition. Okay. So, this is what is called lossless join property for decompositions. Now, this is truly an undesirable kind of situation. We do not want this. Whenever we do a decomposition, we would like the information to be preserved in the decomposed relations. So, when you take the decomposed relations, okay, join them, do a natural join, you must get back exactly what is there in R. You should not get additional tuples. There should not be any additional tuples. If there are additional tuples, then we say that there is actually a loss of information there. So, we call such a decomposition as a lossy decomposition. Okay. Now, you can actually, if you carefully watch this, this B is the common attribute for AB and BC, and B neither determines A nor determines C from a functional dependency point of view. B does not determine C, B does not determine A, and because of that, if it has certain some values, the other values can be anything, and because of that, you can see that when you do a join, you will get some spurious tuples. Okay. So, there is some issue involved in this. And so, people have studied this property and then said that okay, this kind of phenomenon is happening and we do not want this kind of thing to happen whenever we do decompositions. So, we have to be careful about these decompositions. We should always put this condition saying that we must get lossless decompositions. Our decompositions that we are trying to get in order to achieve certain normal form should always be lossless. So, that is the kind of okay. The other one property, the desirable property for decompositions is called dependency preserving property. Okay. So, here also let me now define what exactly are we talking about. Let us take a decomposition D which has some k number of components, we can now call it probably like that. It is said to preserve a set of functional dependencies here if the union of phi r1f, phi r2f, phi rkf, the closure of that union is exactly same as the closure of it. Okay. What is this pi r1f? The pi r1f, normally we use pi for projections, data projections, but here we are kind of slightly misusing the notation because it's kind of convenient to use it. We are now applying it on functional dependencies, set of functional dependencies. Okay. So, it is defined like this: the set of all functional dependencies that are there in the closure whose left hand side and right hand side are part of this Ri. Okay. Ri is a bunch of attributes, subset of the attributes of R. Okay. So, when you take the set of all functional dependencies that are supposed to hold on the original scheme R, that is the F closure, it makes sense to take those FDs in that closure, which contain the attributes that are there in Ri and then put them separately as those applicable for Ri, and that is what we are doing here. So, phi Ri F, okay, you can call it as F underscript I if you want to, is the set of all those functional dependencies in F plus whose left hand side and right hand side are both part of Ri. They do not contain any other attribute other than what is there in Ri. So, they are in some sense applicable to Ri only. So, okay. So, that is what we call them as the functional dependencies that are in some sense applicable to a particular scheme Ri. Ri is a subset of R, right. So, we can call as a projection of F onto Ri, because normally we talk about projections only for data, but now here we are projecting the functional dependencies onto a subschema called Ri. Okay. Now, the decomposition is said to preserve the functional dependencies if you take these projections, take a union of all these projections and they take their closure. If that is equal to the F closure, that means all functional dependencies are available either directly or in each of these Fi's, or they can be derived from these Fi's. If that is the case, then we call this decomposition as a dependency preserving decomposition. Dependency preserving decomposition. So, I have written it here that any FD that logically follows from F must also logically follow from the union of the projections of F onto each of these Ri's. We will call such a thing as this is also a fair thing to ask for, right. You have a bunch of dependencies and the relation instance is supposed to satisfy all those functional dependencies at all point of time, and so the RDBMS is actually held responsible for ensuring that that happens. And so, if now you take a particular relation and then split it into two relations, then the RDBMS should have a way of enforcing that. So, what the decomposition, if it satisfies this dependency preserving property, then what it can do is that I can take the projection of F onto Ri, R1 and R2 and enforce them. It is equivalent to enforcing the original set of functions. Okay, so that is what we want. So, these are the two interesting properties of decompositions that we are looking for. So, we are not interested in arbitrary decompositions of a relation, or we are interested in those decompositions that satisfy these two properties. One is called the lossless join property, the other one is called the dependency preserving property. If you have any questions, please raise them now, because we will then discuss specific algorithms for actually checking for the losslessness. We now need a method of checking whether a decomposition is indeed lossless with respect to a set of functional dependencies. Okay. We need a method to do that. Okay, I have an example here which illustrates dependency preserving. Just have a look at. Here is a simple scheme ABC, and we have FDs AB, A determines B, B determines C, and C determines A. Everybody determines everybody else. It's a cyclic kind of thing. So, we did a decomposition R1, AB and BC. Now, if you take phi R1 of F is all those FDs in F or F closure that are applicable to the scheme AB. So, obviously, A determines B is applicable, B determines C is not applicable because C is not there here, this is also not applicable, but then because of B determines C and C determines A, we have B determines A, and so that is actually applicable for our case. Right. So, A determines B, B determines A will come into picture. In a similar way, B determines C, C determines B will come into picture here. And if you take the union of these two things and take a closure of that, you will see that it is actually equal to this. Not equal to this, it is equal to the closure of this. It is equal to the closure of this. And so, this particular decomposition is dependency preserving with respect to this set of functional dependencies for this relation R. It turns out that okay, we have a algorithm that can check for whether a decomposition is indeed lossless or not. Okay. So, given some scheme R with attributes A1 through AN and given some functional dependencies F, the decomposition R1 through Rm, we are going to answer this question, is B a lossless decomposition. Okay. So, here I am going to present an intriguing looking algorithm, but will not give you any proof for this. Okay. It is an interesting algorithm. So, let me present that algorithm. This algorithm works on a small matrix. Actually, we create a m by n matrix where m is the number of components that are there in the decomposition and n is the total number of attributes that are present in the original scheme. We create an m by n matrix called S, and the column names are all these attributes A1 through AN, and the rows actually are labeled by these relations R1, R2, Rm, the components of the decomposition. Okay. And it is kind of initialized like this. The ith row jth column is initialized to a symbol called Bij uniformly. So all B symbols, but each B symbol is distinct from others because it has subscript Ij, Bij, standing for the ith row jth column. Now, so some of these attributes are part of these schemes R1 through Rm. So that information is captured like this. If some Aj, which is a column, right, if Aj is in the scheme Ri, schemes are in the rows, okay, scheme Ri, then what we are going to do is to set the ith row jth column into a symbol called Aj. So this does not have the notice that it does not have two subscripts, it just has one subscript, the column number. So this is how we initialize this matrix, and then we do something interesting with this matrix. We repeat certain, we actually what we do is take this relation, take this matrix as some kind of a instance on the scheme R and try to enforce all the functional dependencies that are given to us. Enforce all the functional dependencies that are given to us. Ensure that this particular data actually satisfies those functional dependencies. So how do we do that? Is that for each of these functional dependencies, U determines V in the F. What we will do is for all rows in this matrix that agree on the left hand side attributes, U attributes, okay, make the symbols in the right hand side V attribute columns for each V attribute column, okay, make the values same in all those rows. Let us say there are some 3 rows, all of them are agreeing on the U attributes, okay. So take one of these V attributes and then ensure that in that column the same value is existing in all those rows. If you do that, then basically we have ensured that U determines V is enforced on that matrix, okay. So let me elaborate that actually how exactly we will do that. There is a method of doing that. So if any of the rows has an A symbol, what are these rows? These rows are the ones that are having the same values for the U attributes, okay. Now we are focusing on one particular V attribute. We are focusing on one particular V attribute, the right hand side attribute. In that we will look at all the rows, okay. If any of those two rows if any of the rows actually have an A symbol, we give priority to the A symbols. If any of them have an A symbol, then we put that A symbol in all the rows of that column, okay. That will make it same. So if any of the rows has an A symbol for that column, set the other rows also to the same A symbol. Otherwise, that means it does not have that particular column of that V attribute does not have any A symbol at all. So, it has some only this Bij's. Then choose one of them, choose some B symbol arbitrarily and then make everybody else equal to that B symbol. So, there is some non-determinism here, it does not matter which B symbol you choose, take them and then just do that. And you do this for, there are two kinds of things, for each of the attributes V you do this and then go back here and then take up another functional dependency UV and do the same thing, repeat the same thing, repeat until no changes occur to the matrix S. So, this is the algorithm. This almost looks like some kind of magic kind of algorithm. And the what do you do at the end of this thing is that at the end, if there exists a row with all A symbols, then the decomposition is lossless, otherwise the decomposition is lossless. Okay. I urge you to take that example and then try this out actually, or I am giving you some anyway I am going to give you an illustration of this particular. So, at the end of all these changes to the matrix, what we are going to check is that does there exist a row with all A symbols. If that is the case, then D is lossless, otherwise D is lossless. So, here is a example, study this carefully. This is some kind of familiar attributes for you. We have roll number, name of the student, advisor, advisor means advisor ID, then advisor name, course, course means course ID, then grade. And the functional dependencies are roll number determines name, obviously, roll number determines advisor, advisor determines advisor name, and roll number course together determine the grade. These all look very appropriate for this relationship. Now, we are going to do this a decomposition like this: roll number, name, advisor, advisor, advisor name, roll number, course and grade. See, this particular relation, you can see that it has information about different aspects mixed up into one relation. So, if you check based on these functional dependencies, if you check the normal forms, it will not be in an appropriate norm, it will not be in this 3NF etc. Okay. So, it has trouble. So, let us consider this decomposition, which is actually pretty logical decomposition of this, because R1 has information about students, R2 has information about advisors, and R3 has information about students and courses. Okay. So, this is a very neat decomposition of the original scheme. Now, let us just use this to illustrate this algorithm. The algorithm has this matrix where all the original attributes are all there as columns, and then these three things R1, R2, R3 are the rows here. Initially we will fill it up with all B symbols, B14, B15, B16 like that. But then if some attribute is present in a particular relation, we make that into an A symbol. That is what initialization we did. But then that A symbol will be distinct because we will use the column name for that. So, A1 will be used here, A2 will be used here, A3 will be used here. Put A3 in all those places where this particular attribute occurs. Now, let us start enforcing these functional dependencies. After enforcing roll number determines name and roll number determines advisor, what happens here is that, So, there are two rows that agree on roll numbers, A1 is A1. So, originally it had B3 too. Now, we focus on the right hand side attribute, which is name, and then in that column we have one A attribute value, A symbol. So, we will make the other one also equal to the same A symbol and then ensure that these two are same. And same is the case with advisor. We had A3 here, and so we are going to this. And then we will do one more. Advisor determines advisor name. So, now in the current matrix, we find that there are two rows that agree on advisor, A3, in fact all of them agree on advisor. And so, we do an enforcement here, where and one of them has an A attribute, that means A symbol, and so we replace the other B symbols with that A symbol. So, now suddenly we find that last row has all A symbols, A1, A2, A3, A4, A5, A6. And you can also see that there is no more changes that can occur in the matrix. And so, it is actually a lossless join. This kind of looks like magic, right? I mean, there is no, I haven't presented any particular logic as to why this algorithm should work, and I am not going to present actually. I leave it to you to kind of try and figure out by consulting some foundational books on relational databases. In particular, the proof of this particular algorithm makes use of a variant of tuple relational calculus called domain relational calculus. And is present, the proof is present in Jeff Willman's Principles of Database Systems book. So, I am not going to present the proof to you, but I leave it as something which will intrigue you to go and figure out why this works. Okay. So, this is how you can test for lossless decompositions of properties. So, we will stop here. Let me just conclude by saying that this particular algorithm is needed when you have more than 2 number of components in the decomposition. If there are exactly 2 given scheme F and then given set of functional dependencies, the decomposition R into R1 R2, just 2 of them is lossless with respect to F. It is a simpler check that we can do is that R1 intersection R2 determines R1 minus R2, or R1 intersection R2 determines R2 minus R1. If this happens, if any one of these things belongs to F plus, then such a decomposition is lossless. This is another interesting property of these decompositions. So, this is easier to check, you do not have to go through an elaborate algorithm for doing this. So, for example, our decomposition of grade info into roll number, course grade and roll number, student name is indeed lossless, because the common attribute that is there between these two things is roll number, and roll number determines student name, which is R2 minus R1. And I urge you to check this condition on the example that I gave you, which has ABC and then it had spurious tuples. Okay. So, okay. So in summary, what we have done today is to observe that there are some interesting properties that we desire for decompositions. These are called lossless join property and dependency preserving property, and we have defined them formally, and then we have looked at an algorithm for checking lossless dependency property for a decomposition. Okay, good. So we'll stop here.